Okay, so we are actually discussing this ISS paper 2022, paper number 4, and I was discussing this section D, statistical quality control portion in my last class, and I have already discussed question number 7A, part 1, 2, question number B, 7B, 7C, part 1, 2. We are about to start question number 7D. We have just started what was capability ratio, process capability ratios, and we have not completed the discussion. So I'm going to start from question number 7D. So just repeating the question, I hope the screen is visible clearly. So 7D says, what do you mean by process capability? And explain the different measures of process capability and write their interpretations. And this is a 10 marks question. So we can guess a partition of 3 plus 7, or maybe a 4 plus 6. So the partition is not given. Obviously, the definition of process capability will not contain more than 3 or 4, and they explain different measures, and their interpretations will have more than 3 and 4. So this is how we can divide the portions, and then we can actually explain our answers. Okay, so this is my ISS paper 4, and we are actually going to write question number 7D. This is my group D. Okay, question number 7D, group D. So what do they mean by process capability is? So I am defining what is my process capability. Process capability, it is defined as statistical measure of the inherent process variability of a given characteristics. So basically, this is inherent process variability. This word is very important, inherent process variability, because we know that the process has different kinds of error and or different kinds of variability. One is like can be is beyond our control, and one can is the we can actually control it. So the inherent process variability of a particular process or statistical measure to measure this inherent process variability of any characteristics is known as process capability. So under this process capability analysis, we actually have two measures. Number one is proportion of non-conforming items. So, like, this is how we get the proportion of non-conforming items. So, we can have some one-sided specification. Suppose we have one-sided specification. What is this one-sided specification? One-sided specification is, I am actually finding out this proportion of one-sided specification. Example is, suppose x is greater than some s1. This is my one-sided specification. I am writing this proportion of non-conforming items is equals to probability x greater than s1. Okay, so that means like if x is greater than s1, then this probability of that is the probability that the items are non-conforming. So criteria that a item will be considered to be non-conforming is that if this is greater than s1, some s1. So obviously we are assuming that x follows normal, and basically then the probability of these non-conforming items or proportion of these non-conforming items is basically this proportion of this thing. So that can be written as 1 minus capital phi of S1 minus mu by sigma, assuming that x follows normal, and that is basically sum denoted by small p, say. Okay, so if mu and sigma are actually known to me, then we can easily estimate p. If mu and sigma are known, then we can easily estimate p, and the estimate of p is p hat equals to 1 minus capital phi of S1 minus x double bar by r bar by d2. And you know, from the range chart we get the estimate of this mu, sorry, from the mean chart we get the estimate of this mu, and from the range chart we get the estimate of this sigma. So we get the estimate of, basically we will be writing, we get the estimate of mu and sigma from x bar R chart. And the underlying assumption for x bar R chart was that x will be normal. So this is what capability ratio is. So here this is how we have obtained, or what we can get the estimate of p as p hat equals to 1 minus capital phi of s1 minus x double bar by s bar by c2. Here we are saying that we get the estimate of mu and sigma from x bar S chart. So we can use R or S chart for this standard deviation, and this estimate of mu is going to be obtained from the mean chart, basically. Okay, so this is what how we have obtained this proportion of non-conforming items. Next is my process capability ratio. My measure number 2 is process capability ratio, and this is one of the important measure. So this actually is denoted by PCR. Process capability ratio is this. PCR is equals to S2 minus S1 by N2 minus S1. N1, sorry. What is this S1, N2, N1, N2? Where this S1 is we all know about specification limits. This S1 is lower specification limit. This S2 is upper specification limit. This N2 is upper specification, not sorry, this S2 is upper NTL, and N1 is lower NTL. So the difference between S2 minus S1, that is the upper and lower specification limit, and the difference between the upper and lower NTL is going to be the The ratio of these two is my process capability ratio, where NTL stands for natural tolerance limit, where my NTL stands for natural tolerance limit. So this is how we can obtain two different measures of process capability. So this is also can be simplified as, we know that the natural tolerance is 3 sigma limit. So we can also simplify this PCR as S2 minus S1 by 3 sigma minus of minus 3 sigma, which is S2 minus S1 by 6 sigma. Okay, so this is how we can actually uh, find out the process capability ratio. So what are the interpretation of this? So interpretation says that PCR greater than 1 implies this is highly capable, and PCR less than 1 implies not so capable or incapable. So these are the two interpretations of process capability ratio. Next, we will move on to the next question, which is question number 7, part E. What is a CUM-SUM, that is cumulative sum control chart? State its advantages and disadvantages. So basically, this for CUM-SUM chart, I will refer a PDF, which is this one. So cumulative control chart is something which is this one. What it actually do, this control chart actually gives you a cumulative control chart is a type of control chart used to monitor small shift in the process mean. It uses the cumulative sum of deviations from the target. So if you can see the chart, so it is actually the small shift whatever we have, that can be incorporated by accumulating the sum of all the values. So that the main target of this is doing this small shift, the changes or monitoring this small shift. Monitorization of small shift changes in the process mean is called CUM-SUM chart. So since it is sum, so obviously it will concentrate on process mean. The CUM-SUM chart actually requires two parameters. One is K, is the sigma unit, and it is by default set it as half. Another one is H limit, which is the sigma unit, which is H equals to 5. Okay, so this is the basic what CUM-SUM chart actually looks like. Then we will move on to this actually one paper which I am actually referring from CUM-SUM chart, where we get the formula of CUM-SUM chart. This control chart's formula is this thing. So this xi bar is summation over j xij by n. So for any ith subgroup, for any of the subgroup, we get this particular mean. So we know we have obtained different subgroups, and for the ith subgroup, this is the ith subgroup mean. So this is my ith subgroup mean. So estimating the target value, so the joint mean will be summation over I of this whole thing, because this is a suffix I. So this is my grand mean. So, and next what we are actually going to do, the sigma role what we are playing over here is this thing. Sigma hat is S bar by C4. This is the mean of the standard deviation, and this S bar is summation over Si by K, and C4 is S expectation of S by sigma. So this calculation of expectation of S is this, and C4 is actually taking the value this. Right? This is the gamma function, these two, and this is the square root function. So this is my CUM-SUM chart, and estimating sigma weightage approach is this one. So this is how we calculate the come sum chart. And the advantages is what I told you, that it helps you to find the small shift change in the process mean. But the disadvantage is that it is difficult to obtain the small shift change, since we are taking different small portions of the data, like we are taking subgrouping the data, so obviously there will be shift. So naturally it is very difficult to obtain that, and estimation procedure is very complicated. So these are the possible values of the come sum charts. Next, moving on to the next question, question number 8. So they question number 8, explain how would you interpret shoehorn control or be when given and are they are not given. So we know that the control charts for uh, the fraction defective. First, we will go for the second portion of the question, that is 8 part A part 2. Then we will move on to 8 part A part 1. Okay. Control chart for fraction defective, we have already discussed this thing, that number of defective is the NP chart and fraction defective is the P chart. So another name for control chart for fraction defective is known as control chart for proportion of defective. Okay, so this corresponding, the correct chart is known as my P chart. So how we are going to obtain this chart? First, I am going to make a similar table. Before that, I need to define something. Let P denote proportion of defectives in a manufacturing process. So now we will go for the chart, that is subgroup number. We have M subgroups, subgroup size. We are taking all equal subgroup size, and the subgroup size is N. Next is number of defectives, that is D1, D2, Dm. Now we will go for proportion or fraction defective. It is D1 by N, D2 by N, Dm by N. So this some Di by N in general. So we can write for each I some Di by N is basically the fraction defective. So instead of n, what I can do, I can find out the definition or distribution of di. This di follows binomial n comma p for I running from 1 to m. because di is the number of defects, and number of defects obviously going to follow binomial n comma p, with p is the proportion of defects. So that implies expectation of di is equals to np, and variance of di is equals to np into 1 minus p for all I. Now we will go for the fraction of defective distribution, that is a distribution of di by n. So which is very easy, which is going to be sort of Bernoulli. We can easily obtain it from over there, but we are doing it in a different way. That implies expectation of di by n is equals to p, and variance of di by n is equals to n into p into 1 minus p by n square. That is going to give me p into 1 minus p by n for all I. So this is the mean and variance. So in general, we will have upper control limit as p plus 3 into p into 1 minus p by n, the square root, that is mu plus 3 sigma. The central line as p, the lower control limit as p minus 3 into square root of p into 1 minus p by n. This is the general three lines what we can have. Under these situations, what they said, that if there are, how we will obtain the procedure, this is already done. The standards are given and standards are not given. So we will go for case 1, where standards given. Standards given, let p equals to p naught given. If it is given, then my UCL will be p naught plus 3 into p naught into 1 minus p naught by n. My CL will be itself p naught, and my LCL will be p naught minus 3 into p naught into 1 minus p naught by n. Next is my case 2. Standards not given. So in case of standards not given, we have to estimate p. Let p hat be the estimated value of p. So how we are going to obtain p hat value? P hat is nothing but the grand mean of di, 1 by mn summation over di over I, 1 to m. So this is my p hat. So under this situation, the UCL is p hat plus p hat into 1 minus p hat by n, the square root. The CL is p hat, the LCL is p hat minus p hat into 1 minus p hat by n. This thing. So if the standards are given, we are going to proceed like this. If the standards are not given, we are going to proceed in this way. So this is how the fraction defective charts is actually going to be obtained for this particular situations. Now coming for the 8 question number part 1, they said to get the different control limits proposed by Shewhart. So we know that the rational subgrouping, the main important concept. Let me go with the question once again. This is 8A part 1. So let me number the question properly. Just a minute. Yeah, I have numbered it properly. This is 8A part 1. So this was the question that explain how you interpret Shewhart control chart to decide whether the process is under control or not. So we know that we have a concept which is called a rational subgrouping. So this rational subgrouping concept is very important, and this term rational subgrouping was introduced by Shewhart. So that's why this is called Shewhart control chart, and this rational, and this actually going to tell you that how we can actually obtain the control charts which can tell you. So variation, so there are two terms related to this thing, that's why this is a 10 marks question, but we have to define both the things very briefly. So what are the terms we have to go through in this context? Number one is my variation. What is my variation? Variation is the regardless of how well designed or carefully maintained the certain amount process is, there is a certain amount of inherent natural variability will always exist. So this we can actually say that irrespective of, okay, let me define it like that. uh, Regardless of how well designed or carefully maintained and controlled is is the process, though there will be some inherent natural variability which will always exist. Okay, so some natural variability means which we call the random effects, which always exist. So, which is beyond my control. So, which is actually beyond the operator's control. This natural variability is what we can say is random and beyond the operator's control. Is random and beyond control. So in this case, so the this is what we call the allowable variation in our statistical control. So this is known as allowable variation. Allowable variation. What is my non-allowable variation? The variability which occasionally occurs. The variability which occasionally occurs and is, or not is, basically we can say, and can be controlled, and can be controlled, and can be controlled basically, which is not beyond my control and non-random. What are this? Number one is maybe improperly adjusted or controlled machines. Number two, operator error. Number three, defective raw materials. Okay, so these are the things which is not beyond my control or the operator's control. It can be controlled by the manufacturer. So these are some kind of variability which are compared to which are non-random and can be able to, like, we can able to control this thing. So these are not actually allowable variation. These are known as non-allowable variation. Okay, so basically these are the one thing under variation which comes next. What we can actually say is rational subgroup. My next term is rational subgroup. This rational subgroup is also a very important term. How is it important? So this Schuhart actually he framed this particular term rational subgrouping because in a process control the collection of the sample data according to the Schuhart is called the rational subgrouping concept, because the collection of the data is very important. Because what we actually do, we have to collect the data uh, in different subgroups, for which between the subgroups the difference should be maximized, and within the subgroups the difference should be minimized. So what is rational subgrouping? This actually term, the term rational subgroup is related to sample data collection termed by Schuhart. Okay, so what he said that the presence of the assignable causes or variation, so variation and differences between the groups must be maximum, and within the groups must be minimum. So this is what called the rational subgroup concept. So based on these two things, what we have, or what was the conclusion taken based on these two things, that how we can do this or how we can utilize this concept, the result came out as we have defined the control charts as a result. So we actually, he said that we can define something which is called control charts, we can, which can tell me that which products are capable for actually specifying the fitness of the quality which are going to be marketed. So what a control chart really is, a control chart is a type of this thing. The drawing is not so good right now. So which has a central line, upper control limit, lower control limit, and here the value of the statistic TI. So what this is the statistic, and these are the subgroup number I. So 1, 2, 3, 4, and so on. Okay, so this is how it proceed. So what is the concept of this thing? So corresponding to each subgroup, we plot the corresponding statistic in this particular chart. And what this chart do? It places this particular value of the statistics in this chart, and there is a presetted scale as per our choice, which is this UCL, LCL, and this. Whenever the point false, the exact thing, the exact quality of the product is this if the point falls over here, sorry, if the point is over here. So these are the exact good quality products. These are the exact good quality products, this blue one. Okay, so if the products lies over here, here, maybe on the upper limit, maybe on the lower limits, the green ones, they are still are like, there we are giving a bound, like okay, this is not, we can't say that this is the exact pass mark. We are just giving a upper and lower limit, that if they falls within this boundary, they are can making the quality specification. But points falling outside this upper and lower control limit, the red ones, they are not like passing the quality test, and they will not going to be marketed. So these lots or these groups are basically not cannot be marketed, because they are have not qualified the product quality test. So this is how the control charts determines the and process monitoring technique. So this is what I have telling you in brief, so you have to write it in details. So and as long as the point falls inside the band, the process is under control. And as the point started falling, at least if one point starts falling outside the band, then we know that we can suspect that there is some error, maybe inherent variation, maybe allowable, non allowable, and then we need to put some concentration on the process, and then we can see and judge. And if the point started falling outside this band of LCL and UCL, then obviously there is a problem in the process, and the process is not running properly. And if we see a random pattern also, so this is not only the one case, there is some special case as well. Suppose we have this UCL, this CL and LCL, and the points are like this. Every point is within the limit, within the band, but they are giving you a pattern, a particular random pattern they are giving you. Then actually if they are giving you a systematic and non-random pattern, then actually this is also an indication that the process is not under control. So this is also a indication that the process is not under control. So you have to mention these 2 points as well. And mathematically, we have to define that the 3 sigma limit for the process control is specifically if they ask you for the question of more than 10 marks. For the 10 marks, this much question is enough. Now we have some questions from the product control, that is write a note on OC curve for the control chart. State the situation for the exponentially weighted moving average control chart, and also determine its control limits. Mention the situation where acceptance sampling is most likely to be useful. State the advantage and disadvantage of acceptance sampling. Explain the operation process of single sampling plan. Also determine the effect of N and C on the OC curve. Next, the last question is explain the operating procedure of a double sampling inspection van. Derive the OC curve, average sampling number, and average total inspection. We will start with the OC curve and the product control. So now till now whatever we were discussing is basically my process control, which was I told you that the interest of the manufacturer. Now we will go with the product control, which is totally the interest of the consumer. So the product control, what they actually says, is known as the like the it actually deals with the on the interest of the customer. And here we have to deal with the few terms, like already you have heard of few terms, they're present in the question: ASN, ATI, OC, these kind of things. So we will first go with the proper definition what they are asking for. This OC curve in the control charts, or this operating characteristic function and OC function with OC curve. So the probability of accepting a lot of quality P under the sampling inspection plan. So before we go for this the particular thing, we need to know what is sampling inspection plan. Okay, so a sampling inspection plan is actually a procedure which is basically we will go for, it's a kind of sampling. Okay, so this under this procedure, let me give the question number. This is 8B. Okay. So 8B says that why we don't go for this 100% inspection. So if we have a particular lot and if we go for the 100% inspection, it's not possible to go for 100% inspection always. Because suppose we are inspecting firecrackers or maybe life of a bulb. So if we are burning all the firecrackers, we are left with zero. So this is similar to what I said is sampling theory. So, like sample survey, what we can say, not sampling theory. So, 100% inspections are not always possible. So, what is my inspection is sampling inspection is my this thing. This is an incoming lot. This is the proportion P what we are getting, and incoming lot size is N. Now we can do the inspection over here. And what kind of inspection we can do? One thing, we can do complete inspection, that is 100%, which is not at all recommended. Not recommended. Or there comes the partial inspection. Partial inspection, which is actually known as acceptance sampling. Okay, and then we have the lot of outgoing lot, name as outgoing lot. So this is what is called then acceptance sampling. Okay. So a procedure typically known as acceptance sampling is generally employed with a lot which is sentenced as worthy of acceptance or not. So basically a lot after the manufacturing is going to be accepted by the customer or not is basically called acceptance sampling. Okay, so and is basically, and the tool we carry out for acceptance sampling is called the sampling inspection plan. So let us write the definition. Acceptance sampling definition is a procedure known as sampling is generally employed where a lot is sentenced as worthy of or acceptance or not on the basis of inspection of samples from a lot. So this is what we call acceptance sampling. Next, what is my sampling inspection plan? The tool for carrying our acceptance sampling is the sampling inspection plan. This is what we call sampling inspection plan. So next, based on these two definitions, we can go for the particular definition of OC curve. OC curve. So OC curve is the probability acceptance, sorry, not acceptance, accepting a lot of quality P under a given sampling inspection plan is known as OC function, and it is denoted by is L of P. And what is the OC curve? The curve of P against LP is known as OC curve. The curve of, or rather we should say the plot of, not the curve, the graphical plot of against P gives the OC curve of a SIP. SIP is sampling inspection plan, and the OC curves actually looks like this. This is my P, this is my LP over here, and suppose this is the 1, and here is actually the P bar, the process average P bar. So up to P bar, this will take the value 1. Like this. Up to P bar, it takes the value 1, it is 0, and here somewhere it is 1. Okay, so the OC curve is actually this, and this is the ideal shape of a OC curve. That is the P bar, it will reach the max value 1. Okay, so this is the operating characteristics function of a particular sampling inspection plan. Is this clear?
Yes, ma'am.